So this video is going to be about Avogadro's law. And remember, we have four basic properties of gases: pressure, volume, temperature, and amount of the gas. So what Avogadro's law says is if the pressure and the temperature of the gas are kept constant, then the volume is directly proportional to the amount of the gas. So I'll return back to my balloon example. As you inflate a balloon, as you blow more air into a balloon, the balloon expands because the more gas particles that you're blowing into it need to occupy a greater space. So it's pretty intuitive. This is another one of those intuitive gas laws that's been known for a while. And so let's see if we can't derive the equations that might be useful on a problem. So, like I said, if the pressure and the temperature of the gas are kept constant, so those two are constant, then the volume of the gas, V, is proportional to the amount of the gas, N. So I'm going to turn this proportionality into an equation and say that V is equal to a constant of proportionality, K, times N, the amount. Divide both sides of the equation by N, and you get that V over N is equal to the constant K. So that means, like I said, as long as I keep the pressure and the temperature constant, if I have two different conditions with two different volumes and two different amounts, the quotient of the volume to the amount is always going to be the same constant K. So, in other words, V1 over N1 is equal to V2 over N2. So let's do a problem, shall we? So suppose I have a gas, and I have 10,000 moles of this gas. And suppose the volume that this 10,000 moles of gas occupies is 6 liters. If I were to change the amount of gas, the amount of moles of gas, to, let's say, 100,000 moles. So if I increase the amount to 100,000 moles, what is going to be my new volume? So first of all, we can just intuitively reason that the volume should be larger. It should expand because volume and amount are directly proportional, and since we're increasing the amount, then that should lead to an increase in the volume. So it definitely must be larger than 6 liters. We know that. So let's write down the relationship again. We have V1 over N1 equals V2 over N2. So we're looking for V2, so I'm going to divide both sides of this equation, or excuse me, I'm going to multiply both sides of this equation by N2, and that'll lead to V2 equals V1 N2 over N1. So now all we have to do is just plug in the numbers. So we have V2 is equal to V1, that looks like 6 liters, times N2, which is 100,000 moles, over N1, which is 10,000 moles, and 100,000 over 10,000, that's going to be 10. 10 times 6 is 60. The moles cancel. This unit cancels. So we're left with nothing but liters. So that means that our V2 is going to be 6 liters. Excuse me, 60 liters. So there you have it. There is Avogadro's law. Alright, so this video is going to be all about Charles's law. And remember, we have four basic physical properties of gases. We have pressure, volume, temperature, and amount in moles, or amount of gas particles present. So what Charles' law says is that if you keep the pressure of the gas and the amount of the gas constant, then the volume of the gas is directly proportional to the temperature of the gas, and vice versa. So that means that if I were to increase the temperature of a gas, that increase in temperature would lead to an increase in volume. If you keep the pressure and the amount constant. So this is actually, pretty intuitive. I mean, you can try this one at home. If you fill up a balloon with air and hold it over a pot of boiling water, that balloon's going to expand. It's going to increase its volume. On the other hand, if you were to dip a balloon in ice water, then you would see a compression. You would see the balloon shrinking down. So basically what's going on at the molecular level is when you raise the temperature of the gas, you're increasing the thermal energy. And thermal energy is a type of kinetic energy, which is the energy associated with motion. So that means you have the particles, the gas particles moving around more quickly. And the only way for the pressure to remain constant, despite those particles moving around quickly, is for the volume to give out and expand. So that's basically what's going on with Charles's law. So let's see if we can't come up with a couple of equations that can help us solve some problems. So the volume, as I said, is directly proportional to the temperature. So that means that V is proportional to T. Okay? But I don't really like that proportionality symbol, so I'm going to turn this into an equation. And I'm going to say that the volume V is equal to some constant of proportionality that I'll just call K times the temperature. And if we divide both sides by temperature, we'll end up getting the important result, which is V over T equals K, a constant. So remember, all of these conditions are satisfied when the pressure and the amount of the gas are constant. So keep that in mind. So V over T is a constant. So that means if I have two different conditions where I have two different volumes and two different temperatures of the same gas, then the quotient of the volume and the temperature is always going to be the same constant. So in other words, V1 over T1 equals V2 over T2, which is just equal to the same constant. So let's go through a problem dealing with Charles's law. So suppose you have a gas, and this gas is occupying 2,000 liters, so I'm going to put V1 equals 2,000 liters. And suppose the temperature of this gas when it's 2,000 liters is 0 degrees Celsius. If I were to increase the temperature of this gas to 100 degrees Celsius, so if I were to increase the temperature, T2 equals 100 degrees Celsius, so it goes from 0 to 100, then what would be the volume of the new gas? So how much is this, to what volume is this gas going to expand if I increase the temperature from 0 degrees Celsius to 100 degrees Celsius? So let's set up our equation. We have V1 over T1 equals V2 over T2. And our unknown is V2, that's the one that we need. So to get V2 all by itself, I'm going to multiply both sides of this equation by T2. And I'll end up getting that V2 is equal to V1 times T2 over T1. And now it's just a matter of plugging in the values. So I'm just going to plug it in. We'll just put it down here. V2 is equal to, let's see, V1, that's 2,000 liters. T2 is 0 degrees Celsius, but we can't put 0 in here. That wouldn't make sense. That would just give a volume of 0. And the reason why is because anytime you're working with gas laws, it doesn't matter which, you need to use absolute temperatures. So the temperature scale that you have to convert to is the Kelvin scale. So to convert from Celsius to Kelvin, remember we just add 273 degrees. So 0 degrees Celsius is actually 273 kelvins. It's actually 273.15, but for the purposes of this video, we'll just call it 273. So that's V1. That takes care of V1 and T2. So now we have to divide this whole thing by T1, which is 100 degrees Celsius. And if we convert that also to Kelvin, we would get 373 kelvins. And it looks like our kelvins cancel, and that leaves us with nothing but liters. And the new volume, let's see, I think I calculated it. Where did I put that? Okay, yes. The new volume is V2 is equal to 2.73 times 10 to the third liters. So about 2,700 liters. So that means that the volume of the gas increased by about 700 liters, and which makes sense. This is one of those kinds of problems that you can intuitively check. If my V2 is not greater than V1, at least by a little bit, then I know I messed up because, like I said, of Charles' law, they're directly proportional. An increase in temperature should always lead to an increase in volume. So there you go. There is Charles' law. Alright, so in this video I'm going to go over Boyle's law. So the basic idea behind Boyle's law, and indeed behind all gas laws, is that we have four basic properties of gases. And those are the pressure, P, the volume, V, the temperature, T, and the amount, N, in moles of the gas. So with Boyle's law, what we're trying to figure out is, if I were to hold the temperature of the gas and the amount of the gas constant, if those two things are constant, then how do the pressure and the volume depend on one another? What is the relationship between the pressure and the volume if the temperature and the gas, the temperature and the amount are kept constant? And the answer is that they are inversely proportional to one another. So that means that at constant temperature, and if the amount is constant, as one increases, the other decreases. So if I were to increase the pressure of a gas, then the volume would decrease. If I were to increase the volume of the gas, then the pressure would decrease. So let's quantify this in terms of equations and see if we can't derive maybe a couple of special equations that we can use. So we're trying to set up an equation for Boyle's law. So remember that at constant temperature and amount, pressure and volume are inversely related. So I'm going to write that in this way. So I'm going to say that the pressure is proportional to, that's what this sign means. It's pretty poorly drawn, but this is supposed to mean pressure is proportional to the inverse of volume, so 1 over the volume. But I don't really like this proportional sign. I'd rather have a real equation. So the way that we get rid of this and turn this into an equal sign is to just say that the pressure, P, is equal to some constant of proportionality that we'll call K times 1 over V. So we no longer have a proportional symbol, we now have an equal sign, and we now have this constant of proportionality. So these two equations are basically saying the same thing. We can rearrange this equation further by multiplying both sides by V, and we'll end up getting that the P times V is equal to K. And this is a pretty important result, because that means we're now in a position where we can talk about the state of a gas at two different conditions. So if I have two different conditions, so suppose I have the gas in an initial state and a final state. So if I have the gas in a state, we'll call that P1 and V1. If I have the state of a gas in which it's at initial pressure and initial volume, if I multiply those together, then I'll get P2 times V2, which is the pressure and volume of another state of the same gas, which is just going to be equal to the same constant K. Remember, this all assumes that the temperature and the amount of the gas are kept constant. That's very important. For these equations to be valid, those two conditions have to be met. So this two-point form of the Boyle's law equation is helpful because it can be used to solve problems. Any three of these things, P1, V1, P2, or V2, if we know any three of those, then we can solve for the unknown. So let's go through a problem. So suppose I have a gas. I'm just going to say that the initial pressure of this gas is 5 atmospheres. And suppose the volume of the gas when it's at 5 atmospheres is 100 liters. Now suppose I took this gas and I compressed it down from 100 liters to 50 liters. So I decreased the volume to 50 liters. Well, if that's the case, what would my pressure be upon compressing it like that? So in other words, what is my P2? That is what I'm trying to figure out. Well, all you have to do is just use your two-point form of the equation. You can say P1 V1 equals P2 V2, which is just equal to some constant. We're looking for P2, so I'm going to divide the whole equation by V2, and I'm going to get that P2 is equal to P1 times V1 over V2. And P1 is 5 atmospheres, and V1 is 100 liters, and V2 is 50 liters. And the liters cancel here, and we're left with nothing but atmospheres, the unit of pressure, which is good. So 5 times 100 divided by 50, that looks to me like that's going to be 10 atmospheres. So, in other words, if I have a pressure of 5 atmospheres and a volume of 100 liters, if I were to decrease that volume down to 50 liters, then the new pressure of the gas would increase to 10 atmospheres. So they are inversely proportional. So this equation sort of makes sense. So remember, like I said, this only applies if the temperature and the amount of the gas are kept constant. These equations only work when those two conditions are met. So there you go. I hope this helps.